right, let's get this party started. So, as you probably have seen in the abstract of this presentation and the title itself, we're going for the Immortal Postgres Web. We're going to build something that will never die. You'll have to go out of your way to kill it, and it will take a long, long time to do so. So who's this crazy joker in front of you right now? My name is Shaun Thomas. I work for Second Quadrant. You probably saw us sitting around in our very large booth with lots of displays around it. And I'm going to warn you right now, my presentations tend to have copious, numerous, endless puns, and I'm very sorry for that, but it's just in my genes. I can't help it. So you probably don't know who I am, but I've been kind of doing this for a little while. I come to the Postgres Open Conference quite often. I've been doing it since they started in 2011 in Chicago. For those of you who aren't aware, Postgres Open did start in Chicago many, many years ago, and it stayed there for quite a long time, and then it moved to Dallas, and now it's here for a little while. That's kind of fun. I also wrote the Postgres High Availability Cookbook, which is now in its second edition. If anyone has gotten hold of that, mostly I wrote it to kind of help out people who want to build a Postgres that, again, doesn't fall over and die. I initially wrote a lot of it after learning from a company I worked at that was a financial services company, and they couldn't have a system go down pretty much ever. And a lot of those techniques I shared because, as a Postgres DB, I'm like, man, I wish I knew all this beforehand. I could put something together with that knowledge. So I'm like, here you go, have at it. And then I also write a blog article occasionally that gets syndicated to the PG, the Postgres Planet little news feed if you want to follow that at all. I try to get one out every Friday, but sometimes my ability to generate topics has something to be desired. So hey, if you think of something you kind of want me to cover, go ahead and send me a link. I'll give you my business card, and you can find me on Second Quadrant also, and I will make your dreams come true. So let's kind of ease into this before I start throwing stacks together. What is high availability? What actually gives you the attribute of something that's highly available? So these are some elements I kind of pulled out. But aside from these, aside from staying online, aside from just flipping over automatically so you don't have to do manual intervention, aside from having a single access path so you can use one VIP or one CNAME to always get to your primary node wherever it is. Aside from having several optional standbys to kind of share the load and always keep your application up. Can anyone think of something that might be another thing that you'd consider part of high availability? Go ahead and shout it out. I'll just repeat the answer so it's on the video. Very complex? It can be. It can be, but part of the presentation I'm going to get into here is the stack that I'm going to put together will be slightly complex, but it will be far simpler to what you are probably thinking of as far as a high availability stack is concerned. Anything else? No? All right, let's move on a little bit. So I threw in this slide to kind of talk about what high availability is not. So some of these may seem a little counterintuitive, like streaming replication, not high availability. It's a thing you can use to make high availability. Same thing with logical replication. You can use that to make high availability. Multiple standby systems. They're great to have. In fact, they're essential for high availability, but they still don't give you that final step. Robust backups, again, like if you want to use Barman or some other tool to kind of make sure that you always have an online recovery that you can depend on instead of throwing something together yourself and hoping that it works or having to go through your own process of building it. No matter how you get there, it's just still another component. But you probably saw the fast failover I marked as not being high availability. Fast failover, all that really means is you can push a button to cause the failover to occur. It's not automated yet. That last component is some kind of watchdog or element that can fail over for you when you're not around. Your database admin's not always going to be there. Like an infrastructure guy is going to have to respond to a page in the 2 in the morning, and pull that, flip that switch. And sometimes, especially for web online services, you can't really always do that. So just to restate that, high availability is just oh, I forgot the next slide. So, and just like high availability being built of multiple components, business continuity is made of multiple components, of which high availability is one of them. So one of my coworkers actually brought this up, and he made a good point. So I bring up the backups again, because that is one way you can reach these next two elements. So when you're building a high availability system, you kind of want to have a plan of attack. And with each point in your plan, you want to have a time of reaching that state. Like, how long will it take to get these servers up? How long will it take to get these servers up? How long will it take to switch all our CNAMEs? How long will it take to do this, and this? And for each particular element of that, your objective is to reach the point where your business can stay available at all times. Now, high availability of your database is one element of reaching that. So I'm not going to cover any of this stuff, but there are things you need to consider when looking at the whole global picture that you're trying to build. And one of the things that we're doing in this particular presentation is to put together something that can aid in that process by removing some steps from your recovery point objective plans. Because the simpler those are, the faster they can occur, and the easier they are to maintain. So let me zoom in a little bit on here. All right, so generally what we like to start with high availability is one of these guys. It's a very simple setup. All it really is a couple of nodes with something in the middle, say call it rep manager, maybe it's PG pool, something that can monitor both systems and can flip them when it notices one is down. It's very simple, doesn't require a lot of resources, and it works for the most part. Until you start getting more complex and then you want to add a third node and whatever, and then you start to need more coordination. We can do all that too, but for a start, in the first couple companies I worked for, this was our setup, and it was fine. So this is what I like to call the ish principle. It's cheap to set up, it's easy to set up and it works, and it's available-ish because you still only got the two nodes. And if you're in one data center, if that data center goes down, you're not really available, but some companies don't want to pay for all the resources necessary to spread and get true high availability with having lots and lots of servers and multiple data centers and links between them and that kind of stuff. So this is what our esteemed friend over there asked when he was talking about a complicated stack. Pacemaker is the traditional manner of setting up a high availability kind of process. And as you may not see from this graph, it's got a lot more moving parts than I've listed here. It's very hard to set up. That RA thing, the resource agent, there's one built for Postgres. You can write your own kind of that layer that basically tells it how to handle Postgres when it detects that it's down. And this is another thing that you might be thinking of. This actually is one of the, I wouldn't say it's a preferred stack, but it's one of the more popular ones. I've actually seen this specific stack discussed in multiple Postgres opens, and I actually gave one of them myself in like 2012 or 2013. This particular stack, it relies on XFS, DRPD, multiple layers of LVM. You notice all those gray boxes. Those are technically offline because with DRPD, you can't have a truly online failover. It'll take over. Pacemaker will detect us down. It will swap it out. It'll move the virtual IP address automatically for you. It'll do all of that. But you can't connect to the other system because it's technically not up. This one back here that I was talking about with that Postgres resource agent, it's more Postgres aware. So what it will do is you'll actually have node 2 will be online. The only thing it won't have is the virtual IP address. So you can still read from it if you know how to connect to the secondary node. The DRBD approach doesn't have that capability, but still people like it because one thing DRBD does that Postgres can't is block level replication on the file system level. And sometimes your transaction rate is so high, like if you're a financial company, for instance, like the company I was working at before, you need to have, block level, everything is committed is right there up to the last nanosecond. So each approach you need has a specific application that works better for. And like I said, once you start getting more and more paranoid, you start throwing other data centers in there. And say you have Dallas and Chicago. Dallas will have one of these. Chicago will have one of these. And then they'll have a link between them, whereas so the Chicago data center will be replicating off the Dallas data center. And you'll want that dotted line to be a manual failover. Still, it's high availability because your data center is highly available, and if you have your entire stack go down in one data center, you've probably got other problems. Like your whole stack is probably hosed, and you're going to have someone doing manual intervention. This is where the business continuity comes into play. It's to keep your business online, and that's a more complicated plan. So Compose, they are at this conference too. We actually talked to one of the guys yesterday. They built a system to kind of get around a lot of this. Their system is a little more, I wouldn't say elastic, but it works by basically you have, in this particular diagram, we've got node 2 being the kind of central node because 1 and 3 are both subscribed to it and they're replicating off there. And the stack they particularly built for themselves was to have HAProxy act as a way of ferreting connections to whatever Postgres primary there was. And then they used etcd as a key value system, a distributed key value system for a consensus model so that they could have a leader race. So you start one Postgres, it goes and connects to etcd and says, is anyone connected in the primary yet? No? Okay, let me claim that for myself. After that, all new nodes will connect and then find out if there's a master or not, and then they will follow whichever one is there, and then the cluster kind of builds itself. And that was all fine and good. And this is kind of why they did it, right? So we've got 3 nodes instead of 2, so it forces you to kind of have a failover for your failover. So while one failover is down, you can rebuild another one, so you've still got your contiguous 3. And plus you've got what they call a distributed consensus model at that point. You've got a true voting triplet. And that's one of the essential elements of high availability is you have some automated way of reaching a true consensus. Because 2 nodes can't really fail over automatically without a third tertiary system watching them. Well, in this case, the third tertiary system is another Postgres node.
So that's, in some worlds, that's what would be called the quorum.
Yeah. That's what you would generally think of as a quorum. All right, so in this particular case, one of the benefits they got from that particular setup was they don't have a VIP or a CNAME to migrate anymore. You can just connect to any of the HAProxys, and there's no resource to migrate. You just will get to the Postgres system that you're looking for. If you're looking for the master, that's where it'll go. If you connect to the HAProxy, that's the way it's usually configured. And since there's HAProxy connecting to every node, it doesn't matter which HAProxy node you connect to, you'll always get to the primary read-write system. And then etcd was that was their distributed consensus method because they didn't want to write their own voting system, right? They didn't want to write their own quorum algorithms or anything. So they basically stole the one for the key value store, etcd. I mean, it already has a system in there. They've got the key race that they can do in the beginning. They can just insert the key. It gets distributed. They don't have to worry about any of the split brain mitigations or anything else. It just does it all for you. They kind of act as the glue to put everything together. So this is important because I kind of mentioned before, you've got 3 nodes instead of 2, and consensus algorithms require an odd number of nodes. So obviously, you can't have 2 people voting for who's going to win or 4 people voting for who's going to win. You're always going to get a tie in the most pessimistic case. So, and again, with no resource to migrate for the virtual IP address, that's one less moving part. That reduces your complexity, I wouldn't say significantly, but it's enough. Especially with CNAMEs, if you're working across a WAN where you can't really share a virtual IP address. And the other elements you get here is failover in this particular case, because Governor would watch everything going on, you'd have automated failover, the thing you were looking for. And since you had the integrated quorum, that was just something that was there for you. When I say follow is automatic and invisible, it's because in this particular case, when you have, say, one of node 2 that was the master in this case died, and it switched over to 1, well, 3 would automatically follow 1. Like, you don't have to issue another command to say, please follow the new leader. It just does it automatically. And then any new nodes you add to the cluster, since they know they'll connect to etcd and go, okay, well, I'm a completely empty node. It will bootstrap itself from whatever master is the current master. So this is all kind of a dynamic, elastic cluster that kind of survives no matter what you throw at it. So etcd uses the Raft kind of consensus model. They've got a whole paper on it. Some guy wrote his PhD to kind of support it. I'm not a mathematician. I'm not going to talk about any of that. I have no idea how it works. And even if I did, I wouldn't be able to convey it properly. So not a Raft lecture. I'm not going to talk about that stuff. So the next thing out of the gate was Zalando, a shoe company, actually came up with Patroni, which was kind of an augmentation to how Governor works. It's the same model. It works the same way in every way, except you notice those question marks at the bottom. Instead of relying on etcd for the consensus model, it can rely on any key value store. It's a pluggable interface there. So you could be using Zookeeper if you're a huge Java shop. You could be using console.io because it's a very popular mechanism for doing auto discovery. So you can actually plug those in depending on your preference. And it has a lot of other stuff too. A lot of other stuff. I mean, what all this basically boils down to is it's Postgres aware. Like, it can use PG Rewind. It knows, it's compatible to Postgres 10. It knows what's going on with Postgres. Governor was a nice glue to kind of get the whole process working. Patroni takes it to the next level and says, okay, knowing that I'm managing a Postgres resource, what other things can I add? And I got rid of Pacemaker. Probably the most important element of all of this. I actually spent months reading over the Pacemaker documentation, fiddling with our resources, the company I was at, and at the point that I got to where I could actually manage it, nobody else knew how it worked. I was like one of 2 people in the entire company that could even start and stop the thing or migrate resources without the whole thing falling over or going crazy, because it's very aggressive. If you send it the wrong command in the wrong time, it'll reach a state where you'll need someone who's an expert at tearing the whole thing apart and putting it back together so that it's consistent again. Especially when you have DRBD involved and you have to resolve a resource corruption issue. So this doesn't have any of that. All gone. So I'm kind of getting a little tongue-in-cheek here. So is etcd good enough? Yes. Do I hate etcd? No. I'm not trying to discredit everything etcd stands for. It's not some kind of crazy thing. Just give me a break here. This particular presentation is not using etcd for a very simple reason. Maybe, like I said earlier, your company uses a whole different stack. Maybe you're a Java shop. Maybe you've got some preference for some other key value resource you want to use instead. The other issue is etcd and its ilk like to run in containers. And at least from the developer I was talking to of Patroni, one of them yesterday, he was saying that earlier versions of etcd kind of fall over once you get past a certain node count. Newer versions might not have that constraint, but it's great to be able to try other consensus models instead. And this presentation is going to basically show a way to kind of get around the scalability of having, an infinite voter count. Because once you start adding in nodes, if you get past a certain threshold, it might fall over. So this is what we're actually going to build. We've got an HAProxy layer, the Postgres Patroni pairs, and then at the bottom we got one of etcd, Zookeeper, or console. In this particular case, for this particular presentation, I'm going to be kind of using Zookeeper as my model. And yes, this is the actual Zookeeper mascot. It's a guy holding a, let me zoom it out a little bit. Whoop, too much. That guy is the actual Zookeeper mascot. I thought it was a joke when I first found it, but no. So why Zookeeper? The real answer for this is why not. It uses a different consensus model. It's not using Raft. It's using something called ZAB. But it's one of those research backed kind of consensus algorithms. So I wouldn't say it's equivalent, but it does the same job. Really, that last point is what matters. So it's written in Java. It uses ZAB instead of Raft. It's slightly easier to configure because you don't have to use 1,000 command line switches like with etcd to kind of bootstrap the whole thing. It's just got like a couple of configuration files and it just runs. But the real answer is that it doesn't matter. We're not really here to discuss the ins and outs of our consensus model or key value storage layer. It's just one of the things that I kind of wanted to prove you could swap it out, and it would still work right.
You did say etcd works better on the host. So
It does directly on the host. It likes to live on the same host it's working on, whereas Zookeeper is more of a kind of a integrated services layer that you can communicate with from multiple different resources. So if you have a Java shop and you've got lots of stuff using key value stores across your entire organization, then making it so that Patroni can also utilize that resource is just convenient. So in this particular stack, we're going to be using these three pieces, HAProxy, Patroni, and Zookeeper. And they're going to look like this eventually. Notice I took out those question marks and all their alternatives, and now it's just Zookeeper. So using layers gives us a few things that we didn't have before. So like I had mentioned to my esteemed colleague up here, we've got shared resources instead of having to have the same resources on every VM we build. We have a known target, so we can create naming schemes, and we can have the names pre-allocated in our configuration files. We can just point to like a pool of HAProxys or a pool of Zookeepers and just have it work. And that pool can be across several data centers. It can be 3 different racks in our data center. Somewhere it's spread around so that we worry less about one particular machine or resource going away. And then voting scalability. Like I'd mentioned before, some of these algorithms don't like to have more than 7, 11, 23 particular voting pairs, because sometimes the algorithm does a cross comparison across all voting members. So as you increase the count, you get geometric growth of the communication paths, and you don't really want that. So in order to get scalable writes across your consensus storage resources, you want to be able to have a semi-small pool. Like you don't want to go crazy and have like 101 of these things. So this is kind of an example configuration file of what we might want to put in HAProxy to kind of point to one of our Postgres clusters. The TCP mode means it won't try to interpret the stream and look for HTTP headers or anything like that. In this particular case, we're binding to port 5000 for this cluster. And then the backends can be the default Postgres port with a bunch of VMs that are kind of running the actual Postgres service. That port 8008, you'll notice the option HTTP check. What that really does is one of the things that the Patroni provides is a REST interface that says, okay, if I respond appropriately on this interface, HAProxy will go, oh, this node's online. So what this is actually doing is those port 8008s on all the Patroni nodes is basically saying whether or not they're the primary node. And then when HAProxy sees that, it will only send the proxy to the node that's actually the primary, and it will ignore the other two. And then this is that other component. This is my Patroni config. One element of it is, like I'd mentioned, the REST API section. You set, the machine name and then the port it's listening on, and then the broadcast that it's, told to listen on. And those two things go together to kind of put together the HTTP side so that HAProxy can act like a regular vanilla proxy and ignore all the HTML stuff they can do also. So the Zookeeper side of this is a little simpler, and this is kind of my side joke that it's easier to set up than etcd. So here's how you set up Zookeeper. You've got this top file, /zookeeperconf myid, you put a number in it. So if you've got 13 Zookeeper nodes, you just go 1 through 13 in each one. And then in the zooconfig file, you basically make a section where you tell it where all the other Zookeeper nodes are, including itself. So you kind of get a static structure of all your Zookeeper nodes, and then you number them all internally, and then you've got a Zookeeper system. There's no, there is auto discovery, so you can just add nodes to it, and there's other stuff, but that's more advanced usages. So if you want to go to the Zookeeper documentation and kind of look on that yourself, you can get more advanced. This is just a basic, throw together a quick cluster, and it's very easy to do. I was actually kind of shocked at how simple it was. So, and in the Patroni side of that, to kind of go along with this, you can give it a list of all of your Zookeeper nodes and say, connect to these. If one of them is down, connect to another one. If one of them is down, connect to another one. And this way, it will always be able to connect to one of the nodes that are available for the consensus model. So even if there's only one available, the key will still be there to be found and set by one master, and the replicas will try to find, just like the setup I was telling you about earlier, the whole algorithm for finding out which Postgres is the master, which one's the primary, or which one's the replicas, that all still works, even if there's only one voting node left. But they don't have to worry about that. It just kind of, it's a black box as far as Patroni is concerned. So we're going to go a little crazy now. We're going to get a little more advanced. And I'm going to zoom out a little bit because these next slides have big images on them. All right. Maybe that was a little too much. OK. So this is what we've actually built. In this particular example I kind of walked through in my slides, we've got a 3-node HAProxy and a 3-node Zookeeper. And in the middle, we've got a Postgres cluster with Patroni kind of managing each of the primary and however many replicas you want to build. There's a reason I made the image look like this, because we can possibly go further. So let's go back to that HAProxy config file. So my previous config was named like front-end Postgres, and then we had some other things. So I'm adding another one. I'm adding another I'm adding another HAProxy backend forwarder. So the ports are all the same. There's different hosts, and instead of binding to port 5000, I'm binding to port 5100. So the shared resource, I'll also have to share IP addresses, because if you connect to HAProxy, those resources have to be available for you to know which ones are which. Well, I can do that as many times as I want and build this. So since my HAProxy pool and my Zookeeper pools are separate from everything else, I can just keep adding more clusters. I can do this as many times as I want. And so I've got cluster 1, cluster 2, cluster 3, cluster 8004. And that's why in my abstract for this particular talk, I had actually said n elephants went out to play, right? And each elephant is a herd of one or more systems that can be any number of different instances or databases put together. And the reason I built this structure is the company I was working for previously to joining Second Quadrant had something exactly like this. They had a dozen different clusters, each one with anywhere from 2 to 20 replicas. So in order to share all of that, so I didn't have a bunch of competing, etcd setups and having a different Patroni stack for every day of the week, I'm like, well, why don't we just use the Zookeeper we already have? Why don't we just add some maybe HAProxy to those Zookeeper hosts? Because I mean, HAProxy is admittedly not very heavy protocol. And then we can just throw Patroni on the systems we already have them subscribe to this new model, and suddenly all of our high availability stuff is truly highly available. I actually wrote a Django app that I presented last year at the same conference to kind of manage all of them because there are so many of them. Like, you've got to be able to rebuild a replica at a moment's notice. You need to be able to fail over to it. And while their need wasn't particularly in the high availability need because their stuff was all internal, well, why not just add it? Like, if changing these few things gives us the ability to be highly available and to be able to add new nodes whenever we want and have them just adapt to the existing clusters, we can add more clusters to the setup anytime we want. It's all free. But I admit not a lot of companies and organizations have this kind of setup where you have, lots of horizontal cluster groups. So interest would be minimal.
Okay. Would that be something like Postgres XL?
XL couldn't. I'm not sure how XL would work with this. Because the thing is, with Patroni works with single instances, and XL definitely has a tiered approach, where you've got like a coordinator and lots of little data nodes. And whereas you could theoretically set up each data node to be a Patroni cluster, I would be afraid of building the coordination between all that, because each particular data node, if you have like 8 of them or 16 of them or 32 of them, theoretically it could work. I haven't actually built that myself, and the complexity of making that all work with the coordinator is my main worry, because the XL has its own little internal tracking systems for knowing which replicas are at which point. And this approach is theoretically somewhat lossy. Like, when I'd started off this presentation, I'd kind of noticed that DRBD kind of catches everything. Well, the voting system with the Patroni approach is such that Josh Burkus, his presentation yesterday was talking about one of the models you can do to kind of get high availability from your containers and being able to tell what state they're in at any one moment. Well, one of the methods you could use to do that is have your Postgres tell on itself. In this case, Patroni is going, okay, to the key value store, this is my status, this is my status, this is my status. Well, the refresh rate we're talking about here is in seconds. And as we all know, you can have lots and lots of transactions commit within seconds. So for a very, very active OLTP system, this might not be a good model. For an average system, it probably will. It's just the tool. You got to kind of go with what you're looking for. And the reason that matters is because the replica, the slaves that take over, if there's a failover, the one that wins is just the one that's the most recent past the LSN that's been from the master that's most up to date. So it'll take the slave that's the most up to date that's remaining, but it has to be past the last one submitted by the primary for it to fail over properly, or it'll consider the whole system corrupt, and you'll have to manually promote one to take over effectively. So, and again, that's within a few seconds. So you could lose up to a certain number of seconds of transactions, and that's in certain approaches that's fine, in others it's not. So if you're using a Postgres XL system where it has to know the status of every node internally, that might not work, but I haven't tested it, so I couldn't really say. Maybe I'll do that as one of my next steps to try and see if it works or not. So there is more. There is more to this. We're not just done with this whole crazy big setup. So let's add load balancing. So we already know that the primary is taken care of by HAProxy. You can connect to HAProxy and always get to your primary node. But what about those two replicas? They're not just sitting there twiddling their thumbs. They're running and they're online, so why not utilize them? Well, it turns out that we'd created a binding for port 5000 earlier. So now let's just say that one offset from your initial port is the read kind of load balanced read target. So this would be a sample configuration for HAProxy again to kind of create a binding for my round robin balanced connection to all my different nodes. And HAProxy does have a section for checking Postgres. But that particular checker has a bug in it where it keeps connecting, doing the check, and then disconnecting without actually issuing a full shutdown of the socket. So your Postgres logs will fill with a bunch of disconnection errors. Even though they're innocuous, they're really irritating. So it's actually better and easier just to use a regular TCP check, which says, okay, well, if it's on the port, it's probably responding. So in this case, it is very similar to our REST interface, except this time it just checks to see if the port is online. And now, if you connect to port 5001 instead of 5000, you'll always hit one of the Postgres nodes, any of the Postgres nodes. And as long as they're online, then you can read from them. So if your application can make that distinction, you can use the entire cluster. So I know what you're thinking. If you've ever used PGPool, you know you can combine read and write kind of replicas so that you can write activation. So if you like do an update or an insert or a delete, those will go to the master, and any reads will come from any of the replicas that are assigned to PGPool. Well, you can't do that because PGPool only works in replication or master-slave mode. Replication mode because it's actually the one sending the rows to the replicas instead of the Postgres replication stream, so it knows that it can read from any of the targets. And master-slave mode because in order for PGPool to work this way, it has to know which node is the master, because it has to know which one it can send the writes to, right? Or since Patroni is taking care of that for us, we can't actually configure PGPool to work that way anymore, because we don't really know which systems to tell PGPool is the master anymore. So it won't be able to work in master-slave mode. So it can't distribute the read-write activity. So we're basically missing a point if we want to hide the seams of all this stuff. We want to be able to just send a query to one of our 5000 port or 5001 port and have some kind of intermediate layer kind of decide whether it should be a read or a write query. So basically, we need someone to take the load balancing mode of PGPool and make it a separate component that doesn't rely on all the other stuff PGPool does. And then we would have a system where you could just connect to one port, do a read or write, and it will just magically go to the right system in the underlying Patroni cluster. So what else can we do? Unfortunately, application side only for now, unless you want to write your own proxy and then share it with everyone. I highly encourage that, by the way. So the last thing we can do with this is confd is a thing that can actually connect to the key value store we have, and we can template it to build configuration files. So here's an example of that. It's gross. So yeah, confd is great at making your eyes bleed. The templating is not quite what you'd expect from, say, one of those handy-dandy Python, like, template languages that are really easy to read and write. This is kind of ugly, but it gets the job done. This is a template file I made for HAProxy to, every cluster you register, all the keys are there, right? So you can just walk through all of the clusters that are in the Patroni system, and you can just generate entries for each one of those in your HAProxy config files. So then your proxy basically will learn about every new cluster set you add every time, and you'll automatically redirect to them. You could add 10, 100, 1,000, and then you'll just be able to connect to them immediately. The only limitation is we have to create this particular key manually in the key value store, because we would need to know the port we're assigning to each cluster, because they could be running on arbitrary ports on each system we're targeting. We can't just use 5432 for everything. So I've got all the resources I kind of referred to on here on this last slide, but I will now take any questions for the brain dump that I just gave you.
Does this mean you're going to have to rewrite your book?
Actually, no. The second edition has a section on Patroni. I called it the simple stack because it really is a lot easier to set up than the 2 chapters it took me to describe setting up a pacemaker failover system. And the only difference between what's in my book and what's not in this presentation is that I took this kind of to the next level. Like in the book, I kind of described setting up a 3-node Patroni system, and then I kind of left it there. This, I took one level above and say, like, well, you know, if you decouple a couple of things and add confd to do the template management, then you can have a self-maintaining cluster that just kind of grows with your needs, and you have to touch nothing afterwards. But from when you decouple those 2 layers and you have those that middle layer of all your Postgres pair clusters, think about how hard it would be to kill all of that. You'd have to kill every single one of your HAProxy nodes, every single one of your Zookeeper or etcd or whatever nodes, and several of your Patroni Postgres nodes in order to shut it down. And it'll probably still be up somehow. Like it makes maintenance a little more difficult, but luckily Patroni newer versions have a pause and resume feature. You can actually connect each one and say pause, stop trying to manage the cluster while I upgrade this one or do this manual thing, and then you can resume afterwards and it'll take over. If you don't do that, if you shut one down for maintenance, it might actually launch another one, or it might try to bring it back up, or it might do a bunch of other magical things behind the scenes. It's almost as aggressive as Pacemaker is in that regard.
Does Patroni have a way to keep cascading failovers from wiping out all your masters? Like if one goes down and it tries to initialize another one, that one goes down and suddenly you have no more databases left because all initialized.
So Patroni itself doesn't actually have a capability of creating new, new replicas. What it'll do is it'll fail over to one of the existing replicas, make it a master. If that one goes down, it'll just keep doing that until it runs out. So if you only have like 3 or 5 or however many for a Patroni, it'll just run out. So some people have set that up with VM management and containers so that if they see that happening, they'll generate a new container. It'll just keep doing that, endlessly. So you'll want to have monitors for that, obviously. The idea is you can just add more resources to the pool, and it will kind of add them to the fold. Like if you've got an empty node, if you add it to one of the clusters, it'll just bootstrap itself off the master and become part of that cluster. So in theory, yes, you could just keep there. If you had a system that was automated enough, it could add a new node, have it bootstrapped, fail over to it, add a new node, have it bootstrapped, fail over to it, and just keep doing that infinitely until you run out of VMs or they get recycled. But Patroni does not have a mechanism on purpose for adding an old master back in until you do it manually. So if a master is like voted out and it's crashed or whatever, you have to do some manual intervention and then re-add it to the cluster, and it will bootstrap itself or do a PG rewind to kind of make itself compatible with whatever current state of the replicas are. And if it can't catch up, you have to reestablish it as a brand new node, basically.
Does it have a check to make sure it doesn't wipe out all your machines? I mean, we've had problems before where we tried to automate this. You ran like there was like a bug in Postgres or data or something. Every one of those died.
So the question is there any way of keeping it from wiping out your masters? Well, it doesn't actually delete the masters. Like I said, the master that it gets voted out or gets crashed or whatever, it stays in its current state, unless you have a system that automatically erases it and then adds it back to the pool as kind of an online mechanism. So don't do that, and you're fine. You'll always have some master available to do some forensics on at least. And like I said, if it reaches that point where you have to manually step into that manner, like something went crazy and you promoted one, shut down the other, promoted one, shut down the other, and then you run out, well, you have to figure out which one is the most ahead, basically erase that particular key set in Patroni, and then start a new master and have it kind of bootstrap the entire cluster for that set. You have to reseed. But that's a very rare occurrence where you kind of cycle through all of your replicas until you have none left.
The other thing you can do too is, so you can set it to PG rewind automatically if it comes back.
Don't do that. So
But
yeah.
you can do that if it promotes a new master. So if it gets to the last node, like what he was asking about, you're not going to have a master anymore.
Yeah.
So your last node would at least still be available.
Yeah. Like that was kind of what I was alluding to. You can make it so that you will always have at least one online system, and the other two, it can auto rewind once you restart them, but don't do that. It will still use PG Rewind once you start the manual and resolve what you're trying to look for that caused that issue in the first place. But yeah, you'll always have at least one database available to do forensics with to make sure that everything is the way it should be. And unlike Governor, Petroni is fully compatible with PG Rewind, so you have a lot less work to rebuild your replicas. Yeah. What is the latency for failover? So Petroni, it's a configurable setting at the very top of the file usually, where you've got your all the timeouts are defined. I think the default is like 10 seconds. You can crank that down as low as you're comfortable doing, but it's still going to be a number of seconds, and there's a reason for that, because you don't want to have such a noisy polling interval that you're causing a lot of overhead that way. That's kind of why I brought that up initially. Like, unlike something like DRBD, where you're getting like the block level replication like within microseconds, this is more of a fungible way of kind of getting the failover stuff to work.
Shaun, two questions. One, how do you deal with dependencies and false positives in this situation, and how do you test the balloon thing?
Dependencies and false positives in testing. Well, false positives are kind of hard to avoid in any kind of automated system like this. If it gets detected that Petroni's down or whatever, it'll shut something. It'll do a shunt that actually relates to the earlier question of how do you prevent it from cycling through all of your replicas till there are none left. You're just going to have to roll with it, I guess. As far as testing is concerned, what I would do is, since this is an entire stack of stuff, I would set it up initially with just a test cluster of like a PG bench database or something that you can fiddle with to your leisure until it reaches a point where you're comfortable putting more production nodes on it than just a set of test data. Because the automated failover process is something that Petroni kind of works really hard on, and they've got lots of features and they got lots of testers and users that will make sure they kind of integrate any bug fixes. But as far as actually making a stack functional, unfortunately that's left as an exercise as a reader. And Petroni is one of those things that kind of was configured to work in containers a little bit better than, say, as a daemon on a machine. So you kind of do have to write your own systemd file to launch it, or a init script, at least currently. Someone might have like a cheat sheet somewhere or one you can just download, but it's not packaged in any way that it kind of runs as a daemon. Because it's almost like they expect you to run it in a container. And I don't really do that, so at least not in this context. Maybe we can get them to patch the documentation to have that kind of included to help make it easier to set up so it's not so onerous to test. How much time do I have left? I thought my timer says I've got 2, but okay. So I've got 2 minutes. Anything else? All right. Well, it was a pleasure. Hope you enjoyed the amazing stack that I was so excited about, and have fun building your Postgres that can't be killed.